Today's video, you will need in class 26. We are going to be looking at parallel lines again and applying some algebra to solve problems using the new information that we learned in class 25. So we start out today with a summary of the important information from our last lesson. We're going to go back and investigate this picture to remember that this line that intersects two or more other lines is called a transversal. And then when those lines that are intersected have these arrows on them, it means that those lines are parallel. They'll never get closer together. They'll never get farther apart. And so we learned about 4 types of angles that always exist when a transversal crosses over lines. But then we learned specific information about what's true when those lines are actually parallel lines in terms of the relationships that these angles have to each other. So first things first, let's remember what corresponding angles are. Those are angles on the same side of the transversal, so they need to both be above the yellow or both below, and one is an interior angle while the other is an exterior angle. So we could talk about angle 7 and 2, or 6 and 3, angle 5 and angle 4, or angle 8 and angle 1. So I'm just going to write an example down so that you have it to look back at. Angle 8 and angle 1 would be an example of corresponding angles. And in the last lesson, we talked about how that corresponding angle translates to create this other corresponding angle. And that means that those corresponding angles will be congruent when lines are parallel. A translation is a rigid motion, so those angles stay exactly the same size and shape. The second type of angle is the alternate interior angle. The first type of angle gets to be a postulate, and then we switch over into theorem mode. So for alternate interior angles, remember we're going to be on alternate sides of that transversal. So one angle will be above the transversal and one will be below. And then both angles need to be in that interior space, which talks about that space between those intersected lines. So in that highlighted section there. So we could choose angle 8 and angle 3 to be alternate interiors, or angle 2 and angle 5. I'm just going to write down angle 8 and angle 3 as an example of that type of angle. And those, again, we proved yesterday, or whenever you did in class 25, that alternate interior angles will always be congruent when our lines that are cut by a transversal are parallel. Alternate exterior angles are very similar. They'll be on alternate sides of this transversal as well, but they'll be in that exterior space. If you think about this as like being a house, they would be out the front door or out the back door, okay? So angle 7 and 4, or angle 6 and angle 1 would be examples of alternate exterior angles. And those as well will be congruent to each other. We proved that the other day, but you can tell if these alternate interiors are congruent, the alternate exteriors are just vertical angles to those. So they'll be the same size as well. And then our final type of angle was called consecutive interior. Those were angles that were, again, on the same side of the transversal, so both above that yellow transversal or both below, but they also both needed to be interior. So we could select angle 8 and angle 2, or we could select angle 5 and angle 3 to be our consecutive interior angles. And those were the odd ones out. They were different than all the others. And you can kind of tell that if you look at the picture. We don't assume how large angles are based on how they look, but this definitely looks like it's less than 90 degrees, and this looks like it's more than 90 degrees, acute and obtuse. So those are not congruent angles, at least not by the way they look in that diagram. We figured out in class 25 that that particular type of angle is actually supplementary. And if you feel like you won't remember what supplementary means back from standard 2, that means that those angles add to be 180 degrees total. Okay, so for the rest of this in class 25 notes page, we are going to be doing examples using those 4 pieces of information. So if we slide down here to the apply section, I want you to notice, first of all, that we're not only interested in answers, we're also interested in reasons. And that is pretty typical for us in geometry, but it is even more important considering that after standard 6, when we move into standard 7, we will be doing proofs using parallel lines. So one more proof standard for us. And so we want to make sure that anytime we're doing our work, we're practicing those reasons so that when we get to proofs, that situation will just be easier. It'll be an easier transition for you. So I usually start with the reason. If I'm looking at the information provided and I am being given this 65-degree angle down here, I'm going to try to compare that to these other angles that are requested and try to see if I can give those angle pairs a name first. So I'm going to do my highlighting just because visually that helps me out to see what's happening. This will be my interior space. Once you practice, you might not need to do that anymore as you get more used to these words, but I'm going to be consistent there. So if I look at angle 1, the first thing that I'm requested to find, angle 1 and 65 degrees look like they're on the same side of that yellow transversal, but they're not corresponding because they're both exterior, and they're not consecutive interiors because they're not both interior. And so we actually can't use that 65 to find angle 1 if we're relying on the postulates and theorems that we've already learned about. So I'm going to put angle 1's measure on the back burner and move on to angle 2. Angle 2 looks good to me. That is our old friend vertical angles. They're in the same group of angles down here, so we don't need any of our new reasons. We are just going to rely on that vertical angles theorem that we've been using pretty consistently to tell us, oh shoot, I wrote that in the measure of angle 1 slot. Oops, sorry about that. Vertical angles theorem goes down here in the measure of angle 2. We'll get rid of that in a minute. And vertical angles are congruent. So the measure of angle 2 would be 65 degrees. Give me a second to get rid of that mistake and I'll be right back. Okay, sorry about that. When we find a measure, it's usually a good idea to put it on the diagram where it belongs, because then when we move forward and we start thinking about the next angle, like the measure of angle 3, I might be able to use the original 65, but I might also be able to use that angle 2's measure to figure it out. And that's actually the case for this problem. If I try to use my angle 2, I see that they're alternate interior. So you could say alternate interior angles theorem as your reason for knowing angle 3's measure. Or if I look at angle 3 and the original 65-degree angle, they're on the same side of the transversal. Angle 3 is interior and 65 is exterior. So those are our corresponding angles. So you could use the corresponding angles postulate as well. I'm going to choose to use the corresponding angles postulate just to highlight that that reason has the word postulate at the end instead of theorem. So I'm looking at angle 3 and the original 65. Corresponding angles postulate tells me that those angles are congruent when our lines are parallel, which they are. So I'm going to go ahead and fill that in, 65 degrees right there. And then last but not least, I'm going to circle back around to the measure of angle 1. And I'm noticing that angle 1 and angle 3 are right there next to each other. They're making this nice straight line along that transversal. They're in that same group of angles. So kind of like down here, when I used vertical angles theorem, I'm going to use something from the past because I don't actually even need to use my second parallel line for this problem. It's just two little linear pair angles sitting there next to each other. So back from standard 2, we know that linear pair angles add up to be 180 degrees. So we can do a quick subtraction using our linear pair theorem, and we'll be able to figure out now that our measure of angle 1 is 115 degrees. So there is going to be opportunity to use things from the previous standards that we've learned. That's typical in geometry, but we'll also have occasions to use our new information as well. Okay, moving on to example 2, similar ideas, but we're starting to see some algebra pop up. So like the last problem, I'm going to take time to really think about what kind of angles I'm dealing with first. I'm going to focus on that reason because that reason gives me a game plan for how to set up my equation. These two angles are on the same side of that transversal, and they're both in that interior space. So I'm going to be using my consecutive interior angles theorem. And that consecutive interior angles theorem, remember, is up top if you need to reread it, but it tells me that these two angles are supplementary, which means I am adding them together to be equal to 180 degrees. They're not a linear pair. Linear pair would share a side in common, so it would be like 6x plus 2 in this angle, or 70 in this angle. These are pointing at each other, so they're not sharing that ray in common like a linear pair would, but they have the same relationship as a linear pair does. If we go ahead and we subtract 72 from both sides, and we do our division, we should end up with an answer for x. I think I know, but I don't want to make a mistake, so I'm going to double check it on my calculator just like I recommend you do. We should end up with 18 then as our answer for x. So we've got a situation here where we filled in our reason, we found our x, but then there's this statement up here that we're looking at as well. That's kind of like the general equation that we would have used back in some of our previous standards, except we don't have names for these angles. So the best that we can do for this statement this time around is just to write what our original equation was. So we took those angles and we added them together to be equal to 180 degrees. And the reason we were allowed to make that statement, to write that equation, is because of the consecutive interior angles theorem. All right, moving ahead to part B, we've got this double arrow, so we know the algebra is going to be a little bit more complicated. First things first, though, I'm going to decide what type of angles I'm dealing with. So there's my transversal that connects those angles to one another. Here are my lines, which are parallel, thanks to those little arrows. And so if I investigate what I'm dealing with, these angles are on the same side of that transversal. 133 is interior, and x squared plus 33 is exterior. I don't know if I said exterior or interior here. This one's interior, that one's exterior. Those then are going to be corresponding angles. They're both in that kind of bottom right section of their little angle group. Bottom right. So they're in corresponding locations. So the corresponding angles postulate will be my reason. That reason tells me that these angles are equal. They're congruent. So my statement will be that 133 is equal to x squared plus 33. If I go to work solving that, I'm going to isolate that x squared the same way I always do, subtract 33. And the reason why that will work is because I only have x squared terms. So this is going to be an equation that we can solve by taking square roots of both sides. We won't need to factor. The square root of 100 is positive or negative 10. And then I just need to make sure that both of those values are acceptable in my geometric situation. So if I take positive 10 and square it, I get 100 plus 33 is 133. That checks out. If I take negative 10 and square it, I still get positive 100 plus 33 more is 133. So both answers are acceptable in algebra, but also in geometry for this problem. All right, we have a few more examples on the other side of this page, so go ahead and flip that over and meet me back here. All right, it looks like next up in 3A, we have the instructions to find two variables and to also give a reason for each of our answers. So we don't need to write that statement in a blank like we did on the other side, but we do still need a reason for our equations and our answers. So if I get my picture highlighted up there, I don't feel like it's going to be wise to try to write an equation with x and y together. That's going to be difficult to solve with two variables. Although those are vertical angles, so they will be equal, we might hold off and use that later. Let's see if we focus on x first, if we can combine that with the 172 in some way to make an equation. These are on the same side of the transversal. 4x plus 32 is interior, 172 is exterior. So those, again, are going to be those corresponding angles. This time they're both in that kind of top right section of their little angle group in a corresponding location. And so that corresponding angles postulate, I just abbreviated angles since that blank was kind of short, tells me that those angles should be equal to each other. So 4x plus 32 equals 172. We're going to subtract that 32 from both sides to get 140. And then 140 divided by 4 to finish it out is going to give us our x value of 35. We could plug that 35 back in. We should get 172 because we know that that angle is going to be congruent to this one over here. And then we could use vertical angles theorem to justify our equation for y. But since we're learning about new angles with parallel lines, I'm going to see if I can do this 6y minus 44 angle and this 172 in some kind of equation. So if I look at that transversal again, it's now separating those two angles. It's kind of like built up between them like a fence. So that means these are alternate angles. I didn't highlight it, but this would be the interior space. So those angles are both exterior angles. So I could use alternate exterior angles theorem to set up an equation for y. That theorem tells us that alternate exterior angles are congruent. So 6y minus 44 is equal to 172. We're going to end up adding this time. So 172 plus 44, 6y will be equal to 216. And then dividing both sides by 6 to finish it out, we'll end up with y equal to 36. But it would be perfectly acceptable for you to write a vertical angles equation instead. It would look identical and have the same answer. You would just have vertical angles theorem as your reason instead. Sliding over to 3b, we see that double arrow again, so it looks like we're going to have some algebra that we'll need to navigate. Go ahead and highlight my transversal and my other two parallel lines so that can help me visually if I'm still working on these different angle types. This looks very familiar to me, very similar to what we had over here. Those are alternate exterior angles again. So I'm going to use my alternate exterior angles theorem to set these things equal to each other to solve for x, keeping in mind that that little box means that that angle is 90 degrees. So 90 is going to equal x squared minus x. And then I run into a problem because I cannot use square roots to solve if I have x squared and x to the first, regular x. So this is a situation where we're going to have to get this equation to equal 0. And then factoring is going to be the method we use to figure out what x could be equal to. We've reviewed factoring quite a bit this year, but not recently. So remember, we're taking that first number and last number, multiplying them together, and trying to find some numbers that will accomplish that for us, while at the same time, they're adding together to be whatever that coefficient on x is equal to. So there are lots of numbers that multiply to be negative 90, but they need to be relatively close together so that they add to be negative 1. 9 and negative 10 are going to be the answer to that little number puzzle. So that means my factors are going to be x plus 9 and x minus 10. And then as a reminder, we split that and we solve these two little baby equations equal to 0. So subtracting 9 and adding 10 give us our two x values that would be acceptable in algebra world to make that equation true. If I take them back and I check them out in geometry world, they might both give me solutions that are acceptable. They might, only one of them might, or none of them might. So let's check. 10 squared is 100, minus 10 is 90. 90 is equal to 90, so x can equal to 10. Sounds great. This one is a little tricky, so I'm actually going to write it out. -9 squared minus -9. That -9 just replaces the x's. It doesn't replace the subtraction. -9 squared is positive 81, and subtracting -9 means we're really adding 9. So again, we end up with 90, which is exactly what we need. So in this case, again, like on the front side, both of those answers work in geometry as well as algebra. All right, we've got 2 more to finish it out today. So if we slide down here to C, things look a little bit different down here because it's trying to distract us and focus us in on a whole triangle. But if I'm thinking really carefully about my parallel lines, they're hiding right here and right here. Feel free to make them a little bit longer if that helps your brain to see them. And then it looks like this side of the diagram is kind of pointless. There are no angles over there that I'm being asked to focus on. So I'm going to choose to use this as my transversal and then just kind of ignore what's happening over here. So if we're looking at this situation on that side, we have quite a bit of information to sift through, but I'm noticing that 2 of those angles have X and only 1 of them has Y. Just going to cover up that part of the picture so that it's not distracting us. That's a good strategy to use if you feel like you're getting confused by that. So if I focus on these angles with the X, they are on the same side of that transversal, and they're both in that interior space. So these are, to move that to write my reason, consecutive interior angles. Remember, we're writing reasons, not just names, so we need the word theorem attached to that to make it a reason. And if we think back, that's the one where the angles are supplementary, not congruent like all of the others. So we need to add those angles together, 5x plus 4 plus 3x plus 16, and they will total up to be 180 degrees total. Go ahead and combine like terms over there on the left side. We've got 8x's plus 20, and then go about the work of moving that 20 over with subtraction and dividing both sides by 8 to figure out that x is equal to 20. If that's the case, I'm thinking the best thing to do is probably to take that 20 and plug it back in one or both of these places. If you choose to plug it in down here to substitute it, 3 times 20 would be 60, plus 16 would make this angle 76 degrees. So if we were focused on this angle here and the 4y angle, they would be on the same side of the transversal. This angle is interior and that one is exterior, and they're both kind of in the top right of their little group of angles. So those would be corresponding angles. So we could solve for y using our corresponding angles postulate. There is an alternative. We could have substituted our x in here and then used linear pair theorem. So that equation would have looked different, but it will give us the same result eventually. Since I'm using corresponding angles postulate, that means 4y and 76 are congruent, so I'm going to set them equal. And then all I have to do to solve is take that 76 and divide it by 4. Y turns out to be 19. If you had done linear pair theorem, this angle would have been 104 degrees. So then your equation would have looked like 104 plus 44y, equals 180. And then when you subtract your 104, you'd be back to the same equation that I wrote. 4y equals 76, and then y would be equal to 19. Your work, though, needs to match your reason. So if this is your reason, you need to have that equation. If you have this equation, then that reason would need to swap out and turn into linear pair theorem instead. So the key with these is that your reason matches your work. All right, last one to finish out today. A little bit easier picture. Here's our transversal. And then we've got our 2 parallel lines. We can tell because they have those arrows on them. Okay. Again, we have x and y, but we also have a number in the mix. So if we're looking at x, it probably makes more sense to write an equation with the number the value that's given rather than the other y expression. Those two angles are on alternate sides of the transversal, and they're both in that interior space. So the alternate interior angles theorem is going to be our ticket to write the equation that 7x plus 5 is equal to 54, since alternate interior angles are congruent. Subtract 5 from both sides and then divide by 7, and x turns out to be 7. Now we could plug that x back in, substitute it, or realize that this is 54 degrees, so these two make a linear pair, right? Or we could look at these two on the same side of that transversal and both interior. So using our new reasons for standard 6, these are consecutive interior angles, which is also a theorem. And that tells us that we need to make those angles add to be 180 since they're supplementary. If we combine like terms carefully, negative 6 plus 54 is positive 48. Be careful, that negative sign sticks with the 6 when you combine those together. We're going to take 180 next and subtract out that 48, which should give us 132. And then dividing both sides by 12, y will turn out to be 11. All right. Thanks for watching today. We'll see you back in class.